Okay, the derivative of e to the x actually can be developed from the inverse property, or the inverse relationship that e to the x has with natural log of x. But I'm going to just go ahead and just give you the formula. If you want to see where it comes from, you can just read up here, or you can do a little more research. But I'm going to just give you the formula. The derivative of e to the x with respect to x is e to the x. And then the derivative of e to the u with respect to x is just e to the u times u prime, or du over dx. So here, I'm going to do just a couple of derivatives here. If you want to take the derivative of sine x minus e to the x, well, you just take the derivative of sine x, which is cosine x, and then by definition, the derivative of e to the x is simply e to the x. Now here, I'm going to take the derivative of natural log of x plus e to the x cubed. Now we know the derivative of natural log of x is 1 over x. And now this is where, to take the derivative of this, is where we use this formula, the second formula up here. The derivative of e to the x cubed is actually e to the x cubed, which I have here. And then you multiply by the derivative of x cubed, which is actually 3x squared. So the derivative of e to the x cubed is actually 3x squared times e to the x cubed. And then one more here, I have y equal e to the tangent x. Well, the derivative of e to the u, again, is e to the u times u prime. So the derivative of e to the tangent x would be e to the tangent x, then times the derivative of tangent x, which we know is secant squared x. Now a couple notes about the e to the x and natural log function. The limit of e to the x as x goes to infinity is infinity, and the limit of e to the x as x goes to negative infinity is 0. But the limit of natural log of x as x goes to infinity is infinity. And it wouldn't make sense to try to talk about the limit of natural log of x as x goes to negative infinity, but you can talk about the limit of natural log of x as x approaches 0 from the right, and that limit would actually be negative infinity. And you can confirm that on the graph. Okay, so now we're going to evaluate some integrals. So since the derivative of e to the x is e to the x, then of course if you integrated e to the x, you would just get e to the x plus a constant. And likewise, if you integrated the form e to the u du, you would get e to the u plus a constant. But of course you have to make sure that you've got the proper form to apply that integral. So to apply the first formula, that's pretty simple. If you want to integrate 3e to the x minus cosecant squared x dx, well, to integrate e to the x, it's just e to the x. So if you integrate 3e to the x, you'll just get 3 times the integral of e to the x, which is e to the x. And then of course, you know, if you integrate cosecant squared, it actually integrates to minus cotangent. So since you have a double negative there, that would be positive cotangent of x. So the answer is 3e to the x plus cotangent of x, and then of course plus your constant. Now on this example, I have x e to the x squared. So to use this formula that I have up here, I first have to make sure that I've got the du. If I'm going to treat the e to the x squared as e to the u, then I got to make sure I have du. So if e to the x squared is e to the u, then that means that that x squared must be u. So u would have to be x squared, and then du would be 2x dx. Okay, so I don't have the 2, but I have the x dx here. So what I can do is just multiply the inside of the integral by 2 and multiply the outside of the integral by half. And then this 2x right here and the dx right here put together gives me du. And of course the e to the x squared is the e to the u. So now I have that integral in the form of e to the u du. And we know that when you integrate e to the u du, you just get e to the u. So when I integrate that, I get e to the u, and then I have times a half, and then plus a constant. And then your last step is to replace u with the substitution x squared. So I get 1/2 e to the x squared plus c. Okay, now here's another one. In this one, I see that I have e to the secant of x, so I'm going to let u be this secant, that's the power of e, so let u equal secant x, and then du would be secant x times tangent x dx. Well, that's exactly what I have here, because I have secant x here times tangent x, and then of course I have the dx here. So that secant x tangent x dx, that's the du, and then e to the secant x is e to the u. And then when you integrate e to the u du, you get e to the u plus c, and then you just replace u with the secant x, since that's what I used for my u substitution. Okay, so here I'm going to solve what's called an initial value problem. So I'm going to give you this differential equation, e to the y times dy over dx equals 2x. And we're given that y evaluated at 2 equals 0, and x is greater than the square root of 3. Okay, so basically what I could do is you can actually multiply both sides of this by dx, and you can get this formula, e to the y dy equals 2x dx. And then you can integrate both sides of that equation. So if you integrate the left side, you get e to the y plus a constant. And then if you integrate the right side, you get x squared plus a constant. And so you get e to the y equals x squared plus some constant. So I'm really not worried about the C2. You know, you might say, okay, didn't you take C1 away from C2, so shouldn't you have C2 minus C1? It really doesn't matter, because regardless, that's just going to give me a constant over here on the right. Okay, so I have e to the y equals x squared plus c. Now I can take the log of both sides. So remember, I want to solve for y, so I want to take the log of both sides. So I'll take the natural log of e to the y, and the natural log of e to a critter is just a critter, so the natural log of e to the y is just y, and so the y would equal the natural log of x squared plus c. Okay, so now remember, we were given that if x is 2, y is 0. So now we can plug 2 in here for x and get the natural log of 2 squared plus c, and we know that has to equal y, which is 0. So that would be natural log of 4 plus c equals 0. Now, the only number whose natural log is 0 would be 1. So 2 squared, which is 4, 4 plus c would have to equal 1. So 4 plus c must equal 1, and then you can solve that for c and get negative 3. So now we know what the c is. So now we can go back to this equation, and we can replace the c with negative 3, and we can get our final answer for the function. So basically, you just solved your probably your first differential equation. Okay, I'm going to end this lecture here to remind you of laws of exponents for e to the x. So just remember, they actually follow the same laws as any bases. E to the a times e to the b is e to the a plus b. E to the a divided by e to the b is e to the a minus b. E to the negative a is 1 over e to the a. E to the a raised to the b is equal to e to the ab. So if you wanted to prove one of these, it's really not too difficult. Like if you wanted to prove that e to the a times e to the b equals e to the a plus b, then what we could do is we could let x equal e to the a and y equals e to the b. And then if you took the natural log of both sides here, you would get the natural log of x equals a. And if you took the natural log of both sides here, you'd get the natural log of y equals b. And then if you add a plus b together, you would get a plus b equals the natural log of x plus the natural log of y. Now, another way to write natural log of x plus the natural log of y is just the natural log of xy. That's one of your log properties. So we have a plus b equals the natural log of xy. Now, if we raised both sides using base e, so in other words, if I took e and raised it to this power, and then on the other side I take e and raise it to this power, I would get e to the a plus b equals e to the natural log of xy. And so we would have e to the a plus b, and e to the natural log of xy is just xy. So we'd have e to the a plus b equals xy. So now, remember in the beginning, remember I said x was e to the a and y was e to the b. So if you replace x with e to the a here and then replace y with e to the b, you get the final statement that e to the a plus b is equal to e to the a times e to the b. And so, you can prove those others in a similar fashion, but that's how you prove the first law here that I gave you. Now, in the next video, I'm actually going to move on to how to deal with derivatives and integrals of exponential functions and logs that use a base other than e. So you might remember, with e to the x or e to the u, the base is e. But how do you deal with, what if you had 2 to the x or 2 to the u? And in terms of logs, you remember the natural log of x or the natural log of u is understood for that base to be e. But what if you wanted to take the derivative or integrate a function that had the log of x base 3 in it, or the log of some function of u base 3? Then that's what we're going to talk about in the next video.